So what we need to do is we write down all the things that we can have. But what is the first b that we can write down such that this is correct? So I think the first b that we can write down is b3. b3 turns out to be equal to, yeah, let's write it. Let's write it. Oh, but for convolution, this is not the end. So we just have a3 bn minus 3, right? We also want to have what? We also want to have a2, a1, a0. Then what should we do? So I want to add what? I want to add a2 bn minus 2, and then a1 bn minus 1, and then a0 bn, right? To make it complete, then what should we do? Well, yes, well, very good. So this time, for this a, to our convenience, we set a0 to be 0, a1 to be 0, and then a2 to be 0. And then this becomes a convolution. Good. Very good, right? So the first thing that we can write down is actually b3, right? b3 turns, let's see if we can write more. Okay. So let's check. Okay, let's check. Is it true? So let's be ambitious. Okay. Is it true that b0 is equal to, is it true that b0 is equal to a0 b0? Is it true? Am I correct? N, right? N. When n is equal to 0, then we will have b0 is equal to a0 b0, right? Is it true? No. b0 is 1. 1 is not equal to 0. Okay. Forget it. How about b1? So is b1 equal to a0 b1? Oh, yeah, I have b0 first. Okay, so is b1 equal to b0 a1 plus b1 a0? Is it true? Yeah, this is true. b1 is 0, right? And then a1, a0, they are all 0. Good, good. So this one is okay. We can use it. How about b2? Is b2 okay? Is b2 equal to b0 a2 plus b1 a1 plus b2 a0? Is it true? Is it true? Let's check. b0 is 0, right? And then we have a0, a1, a2. They are all 0. So left hand side 0, right hand side 0. So this is okay. Now b3 should be normal. Okay, let's try. Let's check. So what is b3? b3 is equal to b0 a3 plus b1 a2 plus b2 a1 plus b3 a0. Well, b3 is, so this is 0, 0, 0, right? This is 1. So b3, and so this is 1. So b3 is equal to a3. Normal. Okay, actually, this is where our recurrence should hold. Our recurrence, original recurrence here, should hold for every n greater than or equal to 3. But we are now more ambitious. After completing these boundary conditions for our convenience, we find that b1, b2 are also okay. So we are going to list down b1, b2 as well. Okay. Now, what should we do? We do the mechanical steps, right? So the mechanical step is, let's multiply this with x, multiply this with x squared, multiply this with x cubed, and so on. And so this one, you need to multiply this with x. This one, you need to multiply this with x squared. And then for this one, you need to multiply it with x cubed, and so on and so forth, right? And then we add them up together. We add them up. Add. So after adding, the left-hand side will be what? The left-hand side will be equal to b of x minus b0. Is that okay? So b of x minus 1. And the right-hand side, what is the right-hand side? Right-hand side is like you multiply bx with ax. So this is related to this one. It may not be the same, but it is related. So what is bx times ax? So bx times ax, this one is equal to what? This one is equal to b0 a0 plus b0 a1 plus b1 a0, right? Times x plus b0 a2 plus b1 a1 plus b2 a0 x squared and so on and so forth, right? So compare. So right hand side we have this term, and then we have this term, and then we have every term, except we don't have b0 a0. Is that okay? So this one will be equal to bx ax minus b0 a0. Is that okay? Oh, lucky. A0 is equal to 0, so we don't need to minus anything, but this is what we should have. Okay? Good. Then what do we have? What do we have? So this implies ax is equal to, you divide bx on that side. Is that okay? So it is equal to bx minus 1 divided by bx. Or if you like, this is equal to 1 minus 1 over b of x. Is that okay? Okay. We have what? We have bx computed. Bx is equal to that one. So ax, well, okay. So let's see. So it's going to be 1 minus this number. Wow. Yeah, we can solve it. Just solve it. Okay? Good. Okay, now we have these two problems solved. Let's solve one more problem, okay? To test our understanding, okay? Okay, why don't we solve the problem again? Solve the problem again. But this time, with a different type of string. Is that okay? So let's do this. We were going to use a new string here rather than 0, 1, 0. Let's try to use 1, 1, 0. Is that okay? So we try to use 1, 1, 0. Okay. Okay, now 1, 1, 0 will be super easy for the first question. So first of all, let's answer the first question. How many n-bit strings such that 1, 1, 0 occurs at position n? Two to the power n minus 3, right? This time is easy. So if we denote Bn to be equal to number of n-bit string with 0, 1, 0 occurs at location n, at position n, and then we will have Bn is equal to 2 to the power n minus 3 when n is greater than or equal to 3, right? And then we will still have B1 and B2 to be equal to 0. Is that okay? Is that okay? Does that make sense? Okay, good. How about the other part? How many strings such that 110 first occurs at position n? Thanks. Yes, thank you, thank you, thank you, thank you. Yes, thank you, thank you. So, how about 110 first occurs at location n? So let's use our understanding and see whether it works. Okay, so this time we also let an to be the number of n-bit string with 110 first occurs at this position n. Let's do this. So let's take a look at what we have done before. So what we have done before is we look at Bn and see if we can have Bn related to An or the previous terms. So Bn is doing what? So here Bn is counting the case where we have 110 here. Okay. So either this 110 is the first occurrence or it is not the first occurrence. Is that okay? So if it is the first occurrence, then you will have An to be counted. Is that okay? But if it is not the first occurrence, maybe you can the first occurrence is somewhere here. Then what we need is, we hope that in the remaining part, we still have 110 going to the end. Okay, good. So we will have what? We will have Bn is equal to An plus An. So we have, using our logic, so it is like B times B3 plus what? Plus An minus 4 B4 plus dot 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 up to A3 and Bn minus 3. Am I correct? Does that mean? Well, this is exactly the same thing that we have written down. And then what thing? So we have not set B0. So why don't we set B0 to be 1? And then, okay, so we have already B1 and B2. They are both 0. And then if we set A0 to be 0, A1 to be 0, A2 to be 0, then this will become a convolution. Is that okay? This will become a convolution. And then what? And then we will have what? And then we will have the same thing we sum up. Same thing we sum up. Same, everything is the same. So we will still have Bx minus 1 is equal to Bx times Ax. Is that okay? Good. So we still have the same general formula for the relationship between Bx and Ax. This time we have a different Bx. So we will have a different Ax. But it is in general true. Okay? Is that okay? Good. Yeah, excellent. So we now can find out, okay, how many strings such that 110 occurs at position n and also 110 first occurs at position n. Okay, let's try to test our understanding. Let's do the final thing. So conceptually, we know how to solve it. It is just time. Okay? Finally, let's solve this problem. Okay, so now we want to find out how many n-bit strings are there such that we find 010 and then one one zero. And then we find 0 1 0 and then let's try to do this. Having one one zero occurs. So we have two strings such that at position n. So what do I mean? I mean we want to have a string such that we have 0 1 0 appearing somewhere here, and then maybe let's switch it. Otherwise it looks too simple. Let's switch it. Let's have 1 1 0 first and then 0 1 0 in the end. Let's do that. Okay. So how many strings are there that we can find? So that 1 1 0 first occurs at this location, and then after some steps we will find 0 1 0 ending. Yeah. So in that case, suppose that let's see Cn to denote the number of such strings. Okay. So we have what? We have C1, C2, C3, C4, C5 is equal to 0, right? And then C6 would be 1. Is that okay? Then what should we do? What should we do? It's not difficult. It's rather easy. How do I get the string Cn? How do I get a string Cn? So let's say we have An to denote number of strings. Okay. So let's say we have An, and then this is for 1 1 0. The number of strings with 1 1 0 first occurs at position n. Okay, and then we have, let's say we have Bn. This is for string 0 1 0. Okay, which is the number of strings with 0 1 0 occurs at position n. Okay. Okay. So A corresponds to 1 1 0. B corresponds to 0 1 0. Okay. But I will omit the 0 1 0 or 1 1 0 there because we just have this A and this B. Is that okay? So how is Cn obtained? So I have a string of length n, right? So at certain point, I must have, because we need to find 1 1 0 first. So at certain point, we need to have 1 1 0. Is that okay? At the latter point, we will have 0 1 0 ending. Is that okay? So Cn will be equal to, it will be equal to A3 times Bn minus 3. Is that okay? Plus A4 Bn minus 4 plus dot 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 up to A n minus 3 B3. Is that okay? Is that okay? And then what? And then, do we get into trouble? Let me see. Let's see. Does that make sense? Does that make sense? So here we need to be careful actually that we want to complete it into a convolution, right? So we need to add back the terms a0 bn, a1 bn minus 1, a2 bn minus 2. To help that, then it's easy. We can set a1, a2, and a0 to be 0. And then we also want to complete this to make it into a convolution. So in that case, this time we need to be careful. We need b0, b1, and b2 all to be 0. Is that okay? Is that okay? But after that, if we can complete things into convolution, then it's nice. We will have cx. So we will have the generating function. So if we complete things, we will have cx is actually simply written as ax times bx. Is that okay? Is that okay? Okay. So we know how to solve ax. This is the same problem that we have studied before. We know how to solve bx. Okay. This is not the same problem we have solved before. We have solved before by assuming that b0 is equal to 1. But here we want b0 to be 0. That's easy because the latter terms are exactly the same. So we just cross out the constant term and make it 0. So in that sense, we have A known, we have B known, and so we have this known. Is that okay? Okay? Okay, so for this problem, yeah, I didn't give you the solution. Perhaps we will have a practice in our assignment. Okay? Okay, thanks all. So I think that's the end for what I want to say about the recurrence. So next time, so there are a few more topics here in the lecture note slides. They are just for interest. So we can use recurrence to we can use generating function technique to solve recurrence with two indices, like the binomial coefficient. You have C and R. So there are two variables inside. So in that case, we will have a generating function with two parameters, b, x, y, such that x to the power n, the coefficient with x to the power n, y to the power r, this coefficient corresponds to the term CNR that you want, maybe. So you can use similar technique to solve that. So I will not talk about that in the class, and then it is not going to appear in the exams. So next time that we meet, we will talk about a new thing. So it should be methods of proving. So we will look at how do we prove things. Okay, that's all. Thanks. See you next week.